Very good morning to one and all present here. Today, I am going to discuss phase rule part 2. In the part 2, I am going to mainly concentrate on alloy system. The main core subjective of phase rule part 2 is that mainly for the construction of two component alloy system. What the main course outcome is that able to fix composition of alloy system. Student can able to fix composition of an alloy system. Similarly, after fixing the composition, students can able to interpret the phase diagram also. Similarly, in future, students can able to prepare metal alloys of their own. Now we'll start with reduced phase rule. Before that video, I have discussed regarding normal phase rule for one component alloy system. Now we are going to take up alloy system. So why we are preferring reduced phase rule instead normal phase rule? Only one point answer for this. Alloy system does not have any gaseous phase. What it means? There is no loss of material. There is no loss of material. That's it. I have represented here. A solid liquid alloy system has practically no gas phase. For example, we're going to take 1 gram of gold alloy. The alloy of what? Gold, copper, as well as gold. Okay. In market, we are calling it as 91.6%, 91.6% gold. Rest is copper. Is an alloy of gold. Let's take 1 gram of gold. Let's go to that of goldsmith center. Then give to them, ask them to prepare, ask them to make any one ornaments or ring or any chain. Finally, after making that, again they will give that very near to that of 1 gram weight after completion. That means what? There is no vapor loss in it. But if you are going to heat the water for around 1 hour, the same amount of weight you will be getting that now? No, impossible. That's it. We are preferring normal phase rule in the case of water system, but there is a loss in material. Loss of material is there in the case of one component water system. But in the case of alloy system, if you are going to give 1 gram of gold to the goldsmith, after that also you are going to retrieve back how much? Same, near to the top of 1 gram. Understood? That indicates what? There is no vapor loss during a making. Okay, so that's it. I have represented here. In the case of alloy system, we cannot prefer normal phase rule. We cannot use normal phase rule for phase diagram. What is the practical difficulty? The right hand side, I have written that. You just go through that. If I am using that normal phase rule, F is equal to C minus P plus 2. In the case of two component system, we know that now C is equal to 2. So I represent here C 2 minus P plus 2. That is equal to F is equal to 4 minus P. If P is equal to 1, F is equal to 3. If P is equal to 2, F is equal to 2. If P is equal to 3, F is equal to 1. From this study, we can come to know that the maximum number of degrees of freedom for two component system using normal phase rule is 3. That means what? That indicates what? 3-dimensional diagram is must. 3 variables are must. Okay. Is it possible? Practically, it is possible to draw 3-dimensional diagram on paper. Very, very difficult. So that we are preferring normal instead of normal phase rule. We are preferring reduced phase rule. Why? Before the video itself, I have given clear-cut idea that the 2 C minus P plus 2. The 2 is nothing but two variables. Two variables are temperature or a pressure, or temperature or a composition. Two are variables. Okay. So in this case of alloy system, pressure no role to play. Sir, I want to prepare one gold alloy system. Any goldsmith is adjusting to atmospheric pressure to 2 atmosphere, 3 atmosphere? No. Sir, I want to prepare one steel alloy. So for this preparation of this alloy wheel, we need to have that 1 atmosphere instead of 1 atmosphere. We need a 5 atmosphere. Anything is any document is there? No, sir. What is the reason? That's it. No gas phase. If you're going to prepare, if you're using that alloy also, gold alloy or maybe steel or whatever may be the alloy, vapor phase, no loss. There is no loss in the vapor phase. Similarly, whatever with the article you're going to prepare in terms of 1 atmospheric pressure only. Normal 1 atmospheric pressure only. We are not going to adjust that atmospheric pressure. Okay, that means what actually? What it indicates that there is no loss. Here, what it indicates that one more point also I can stress here, there is no vapor phase. Pressure we are going to keep constant. That's it. The F is equal to C minus P plus 2 is get reduced into F is equal to C minus P plus 1. That is why we are calling it as reduced phase rule. What it indicates the one is nothing but temperature only. Why is the temperature? Reason is that, for example, gold alloy maybe of melting point 600. The case of steel maybe of melting point 800. That's it. That depends upon what actually? Depends upon the composition. Depends upon the composition. Temperature is variable. Depends upon the alloy system. Temperature is variable. But whatever may be the alloy system, pressure is equal to 1 atmospheric pressure. Okay, that's it. We are using reduced phase rule. Now you just apply that for alloy system. F is equal to C minus P plus 1. That is a two component system. So 2 minus P plus 1. That is F is equal to 3 minus P. From that we can study if P is equal to 1, F is equal to 2, if P is equal to 2, F is equal to 1, if P is equal to 3, F is equal to 0. By using reduced phase rule, the maximum number of degrees of freedom in the case of alloy system is 2. That means what? Two-dimensional diagram is must. Two variables are must. The two variables are temperature and composition. That's it. Very good. Okay. Understood or not? Yes. Thank you. The next one, we will start with the thermal analysis. Now, I am going to educate you how to construct the phase diagram. Okay, we are constructing the phase diagram based on thermal analysis. What is thermal analysis? Study of cooling curves of various compositions of the system. Study of cooling curves of various compositions of the system. Okay, so that's it. I have represented here two graphs here. One is that for left hand side I'm showing here that is pure system. The right hand side solid A and solid B, there is an alloy system. So just a study of cooling curve only we are going to measure. So take a crucible. You take a crucible, you take any pure gold, 100% pure gold you just take. Rise the temperature to the level of near to the molten state, near to the melting point out of molten state. So indicates that above S. See that now above S, only liquid state only exists, molten state. Okay, allowed to cool down now. Allowed to cool down now. See, just going on allowed to cool down now. But point A is what is the actually what it indicates at point A is liquid state, molten state. At point A, the first crystal of gold is coming out from the liquid system. That is we are calling it as freezing point. That is we are calling it as a freezing point. At A dash, what it indicates that complete solidification is over. Complete solidification. Further cooling, no change in system. That means what? Complete solid phase only exists. So just tell me now, at point S, liquid state only exists. Correct or not? At point S, liquid state exists. At point A, solid and liquid are in equilibrium. At A dash, what is that? Only solid phase exists. Below A dash to X, only solid phase. Further cooling, no change. Okay, if it is pure alloy system, only one break point is there, that is a freezing point. Now I will take now second example of alloy system. You take a gold as well as copper. Any solid A or solid B. I represent solid A, solid B, anything you can take. Okay, see, take that gold as well as copper alloy, rise the temperature to the molten state. At point S, that point S indicates the liquid state. At point S, what is the molten state? That means liquid state. Allowed to cool down. Okay, it's a study of cooling curve, correct? Allowed to cool down. At point A, either solid A or solid B. For example, we have taken copper and gold, either gold or maybe a copper, depends upon the melting point, will come out. Okay, at the B, what is that? Second crystal. Okay, for example, if you're going to consider that at point A, solid A comes out. At the point B, B comes out. At B dash, what will happen actually? Solid A and solid B completely solidified. Complete solidification is over. Further cooling, no change. So, if it is in the case of mixture, the case of alloy system, we are having two breakpoints. First, A, at point A, one crystal comes out for the system. That is that we are calling it as freezing point. At B, two solids and one liquid. That's we are calling it as eutectic point. What is eutectic point? At particular point of B, solid A and solid B, solid B started. Solid B crystallization started. Okay, that means what? In the crucible, solid A plus solid B are gold as well as copper. Corresponding its liquid melt is there. Okay, B does complete solidification. Further cooling, no change. Okay, this is a simple diagram. This based on the principle of study of cooling curve only, we are constructing the phase diagram. Okay, so now you understood, I think so. Now I will take that one perfect example of alloy system, bismuth cadmium system. I will educate you how we are constructing the phase diagram. From that, I will tell you how to interpret the phase diagram of alloy system. Okay, so construction of phase diagram. Example, bismuth cadmium system I given. I have taken, see that now there are 8 graphs I have shown here. You just imagine that in the first crucible, graphite, take the graphite crucible, just take 100% pure bismuth, rise the temperature to higher molten state, then allow to cool down. It's a pure system, correct? It's a pure system. What is that? At around the point, this particular point, 271 degree, that indicates that is a freezing point of pure bismuth. Only one break point is there. Okay, so now in second crucible, I'm going to take 90% bismuth plus 10% of cadmium. So mixture I have taken. So how many points? Two break point. First break point we are calling it as initial solidification temperature. Then TF is we are calling it as final solidification temperature. Okay, so initial solidification 230, final how much? 144. Then third crucible 70% bismuth, 30% cadmium are taken. So again I am seeing that two break points here. At around 60% is there now Ti that is equal to merges. Ti initial and the final solidification temperature is merged into 144. Similarly 50-50. Then similarly consider now 30% bismuth, 70% cadmium, two break point, 10% bismuth, 90% cadmium. Again I have taken finally 100% pure cadmium. You are having only one break point, that is 321 degree. So based on the thermal analysis, what is thermal analysis? Study of cooling curves of various compositions. So that's it. The 8 graphs are showing that various compositions I have tried in the graphite crucible taken. Rise the temperature to molten state, allowed to cool down. Okay. Then we are measuring the initial freezing point and final freezing point of the particular alloy system. So the graph is ready now. From that, we are going to review the consolidated graph. That's it. We are calling it as how to construct the phase diagram. So based on the experimental data, now I am moving to the next slide. We have constructed the phase diagram. What is that? X-axis, 100% pure bismuth and Y. See, the right hand end, 100% pure cadmium. This starts from X-axis, 100 bismuth, 90% bismuth. Let's move on to the right hand side, 0% bismuth cadmium. See here, 100% cadmium. It's left to it moves the left to right. There it's 0% cadmium. So two lines we have taken. Then the temperature, y-axis temperature, based on the data in our hand. What is that? 100% pure bismuth. What is that melting point? First freezing point is that 271 degree Celsius. That's it. I represent here 271 degree Celsius. Okay. Second graph, what it indicates that second graph data 230 degree. Then third graph data 170. Then see that 230, 170. Then followed by 0. 0.0 is 144. Again see that now 193, 257, 300. 193, 257, 300. The last 100% pure cadmium is 321 degrees Celsius. Okay, so now just to take the scale, then draw, extrapolate that line now. Okay, so where it cuts exactly, that is particular point we are calling it as a eutectic composition. Okay, so now graph is studied. So that's based on this only, based on the principle of thermal analysis, we have constructed the phase diagram of a bismuth cadmium alloy system. Okay, so construction is ready. Now we are going to interpret the graphs. What is the information you are going to tell to the society? Because of study, we are studying that right, not only for the purpose of examination, we also educate to our youngsters in the future. They are going to come now. Okay, so that's it now. How you are? What is the information you are going to tell that now? As an engineering student, you should must know that now. As a chemistry student, you should must know that now here. just by seeing the graph. So the construction of phase diagram, okay, thermal analysis, okay, the principle, everything you should must know. As an engineering student, as a chemistry students, you should must know. See, what is the information you are going to get it from this graph? Okay, first point you should must know that now here. What is that? What is that? See that in the fourth graph, Ti that is equal to Tf that is equal to 144. So if anybody is asking you how we are framing the alloys in noodle shops, the noodle shop that see that now while preparing the noodles they will do some of the dhania powder, small powders they will add salt, everything they will add within a fraction of a second. They are not preparing the alloys like not like that just like in noodle shop. People are doing that. Understood or not? So we are preparing us or alloy means what? You cannot take any metal ion just like a mix, just mix it now, just die casting. That is not we are calling an alloy. Alloy means what? It's a homogeneous system. Alloy means what? That is a homogeneous system. So how we are going to get a homogeneous system? At around 90% homogeneous, 70% bismuth homogeneous, 60% bismuth homogeneous. Okay. So alloy means what? There is a 60% bismuth. But in the case of bismuth cut, where it exactly cut the point O called as an alloy. O to A, no alloy. We are not calling it as an alloy, it's a heterogeneity. O to B also heterogeneity. At point O, that is a homogeneous mixture. What it indicates that in the case of bismuth cadmium, I'm going to mix the bismuth cadmium, 60% bismuth plus 40% cadmium is a perfect homogeneous alloy. Okay, what is that particular melting point? 141 degrees Celsius. So we can consider a melting point, a detecting point. So here, why we are calling detecting points is two solid. See that now below the point O, solid bismuth plus solid cadmium is there. Above the point O, liquid melt is there. Correct. So two solid and corresponding is liquid melt are in a equilibrium. So we are calling detecting point. So one more, what is the society information from here? 144. So 144 is nothing but what actually the maximum as an engineering student you should must be able to tell that now the maximum just by seeing the graph, what is the first information you can tell to the society is that the maximum operating temperature for bismuth cadmium alloy system is 144 degrees Celsius. Beyond that, what has happened? Beyond that, what is happening here? The two graphs get split out into the OA and the OB. Understood? Up to 144 is a homogeneous. Beyond that, it is a heterogeneity. This is the usual information you are going to try to tell to the upper society or for your industry. Understood? The maximum operating temperature is 144. So this alloy can be used safely up to what actually 130, less than 10 degree, 130 degrees Celsius. Understood? So regarding examination point of view, I will tell you. What is that? How many graphs are here? That's the same. Last time we have done it for one company. It's the same thing you have to do it. Curve OB, curve OA, two graphs. Okay, two graphs. What is the curve OA name? Name of the curve is a freezing point curve of bismuth. Curve OB, name of the name, freezing point curve of cadmium. Okay, the graph curve OA is in equilibrium with what? Solid. I have represented the triangle. Solid bismuth is in equilibrium with the liquid melt. We're going to apply the rule that is equal to 1 degree of freedom. Similarly, this right hand side also is 1 degree of freedom. Okay, so what it indicates is 60%, 40%. 60% bismuth is highly soluble in a 40% cadmium. Only 40% cadmium is highly soluble in 60% of bismuth. This is a homogeneous mixture. If from that, definitely I have educated you. If anybody is asking that why we are calling it as 916 kdm, 91.6% gold. That's what it indicates. Before that, we are paying for 80% gold, 20% copper. Now we are paying for because of technology, and science. Because of that, we are paying for 91.6% gold. We are paying money for 91.6% gold. Understood? So how we have made? Why we are calling it as 91.6? So as an engineering student, you know now clearly. Okay, at a particular where exactly at the particular point we are calling it as a eutectic composite. At a particular point only 91.6% gold, rest is copper. The particular mixture only homogeneous. Okay, that means what? That is highly stable. Highly stable. Understood? So that's the information you can get it. So now we'll go to the next one, bismuth lead silver system. So now you know how to know how to construct the phase diagram of a bismuth cadmium system based on thermal analysis. Similarly, if you're going for, sir, I want to know about the lead silver system. Okay, just Google it. You will be having that lead silver system phase diagram. Just Google it for phase diagram of lead silver system. I want to know about lead silver. What is that? First, go to the system, sit in the system, before system, write down that phase diagram of lead silver. You'll be having that nice picture like this. Will be there. The engineering student, you know that now. What is information? What is first information you're going to get it from here? So 303 degrees Celsius. Okay, what information you're going to write to society? The maximum operating temperature of lead silver is 303 degrees Celsius. For safer side, the alloy can be used up to what actually 295 degree, less than 10, 295 degree Celsius is the safe to use that solid lead and the solid silver. Okay, examination point of view, what is information you're going to tell that now? The typical graph you have to draw, exam point of view, then you have to tell that curve OA we called as a freezing point curve of silver. The silver, okay, then that curve is in equilibrium with the solid lead, solid silver and the liquid melt. Okay, the 100%, the 96 point A is the 961 degrees Celsius. That is nothing but 100% pure silver freezing point of 100% pure silver, 961 degrees Celsius. Right hand side you can see, left hand side you can see that now 100% pure lead melting point how much 327 degrees Celsius. What is point O? Point O called as eutectic point. What it indicates that below point O solid lead and solid silver is there. Above point O liquid melt is there. That means what? Two solid corresponding its liquid melt are in equilibrium. That is we are calling it as what? Eutectic point. So eutectic point means F is equal to how much? F is equal to how much is 0 degrees of freedom. What it indicates that 9.2 called as what? Eutectic composition, 97.4% lead plus 2.6% silver. That particular mixture only is a homogeneous. It is a homogeneous. That means what? Ti, initial solidification temperature is equal to final solidification temperature. Initial and final is equal to how much? Around 303 degrees Celsius. So at a particular point is called as alloy. Before that, left, then right. We are not going to call it as an alloy system. Okay, sir. So this is the information you are going to tell for examination point of view. That's it. I represent here. Curve OA, the pure silver melt 961. Same you can get it from graph. Addition of lead. Okay, addition of lead to lower C freezing point. Correct. Therefore, AO called as freezing point curve of silver. Along the AO, solid silver and liquid melt are in equilibrium. I represented it in the triangle. Hence, system called as a univariate system. Similarly, curve BO also you're going to represent that freezing point curve of lead. Okay, so the area you can see that now. Area, how many areas are there? AOC. This is at AOC one area. That is at above AOB one area. VOC, that is at this triangle is one area. Okay, so whatever with that area, you'll be having a FeCl minus P plus. This is the area of liquid melt. Only one melt is there. FeC minus P plus 2. Sorry, FeC minus P plus 1. Okay, so two component system, only one phase is there. That means what? That is equal to 2 will be there. So that the area, any point, see that now the area above AOC a single phase. Okay, only liquid state. Okay, applying the reduced phase rule, the 2 minus P plus 2 minus 1 plus 1, that is equal to, that is a bivariant system. You can locate any point along the area, you'll be having a below the curve BO, that is 2, solid and liquid phase will be exist. See that now? Here and all, here 2 phase, FeC, just apply the rule here, AOC. AOC, you see that now F is equal to C minus C plus 1, you'll be having F is equal to 1. So it's a univariant system. Okay, so point O called as eutectic point. So two solid corresponding liquid metal are in equilibrium. F is equal to how much? The 0. Okay, sir. This way you can represent that. Now, I clearly I've educated you how to construct the phase diagram. Similarly, how to interpret the phase diagram of bismuth cadmium as well as a lead silver system. Okay, now I will tell you that one more point also, sodium potassium system. Okay, sodium potassium system, just see that now. Sir, any engineers are interested to prepare a sodium potassium system. Just to Google it, we'll be having this type of sodium potassium system will be there. So you can check it out here. What is the information? I see that pure potassium melting point is 60 degree. Pure sodium melting point is 97 degree. As it is, they are stable. We're going to mix it, mix these two, sodium and potassium. What is the main operating temperature here? That is comes down to 7 degrees Celsius. What is the meaning of preparation of this alloy? Okay, unstable at room temperature. Unstable at room temperature. Okay, so just by seeing the graph, you can come to that now the stability of a particular alloy system. So instead of that, no need to waste time in preparing of sodium potassium alloy system. Correct. It is pure now 97 sodium because of potassium 62. After mixing, after mixing means what? After alloying, you'll be having 7 degrees Celsius. No use at all. Okay. So this is the information you are going to try to tell to the society. Okay. Just by seeing the phase diagram. Okay, sir. So I have educated you nicely. I think so. Hope you will be liking this video. Thank you very much for listening. Thank you. Thank you. Thank you. Thank you very much.